On September 26, 2022, NASA's DART mission slammed into asteroid Dimorphos, shortening its orbit by 32 minutes, a jaw-dropping 26 times the shift scientists predicted. We didn't merely tap a space rock, we rewrote the playbook on planetary defense in a single, spectacular collision. Earth just proved it can shove mountains in the vacuum of space. Will we do it again when everything's on the line? Did you know one well-aimed kinetic strike could steer a city-killer asteroid clear of our planet? The DART mission. Space debris just became humanity's new superpower. What started as NASA's most ambitious planetary defense experiment turned into the discovery that could save our planet from extinction. On September 26, 2022, the DART spacecraft slammed into asteroid Dimorphos at breakneck speed, traveling 370 million kilometers from Earth to execute what many called humanity's first real-life superhero moment. But here's where everything went beautifully wrong. Instead of the predicted tiny 73-second orbital shift, something absolutely mind-blowing happened that left scientists speechless and completely rewrote the rules of planetary defense. The double asteroid redirection test wasn't just about proving we could hit a cosmic rock the size of a football stadium. This was our species taking its first serious swing at playing cosmic billiards, testing whether we could actually nudge a potentially dangerous asteroid off course before it ruins everyone's day. Launched back in November 2021, DART had one job: crash into Dimorphos, the smaller moon orbiting the larger asteroid Didymos, and see what happens when human engineering meets ancient space rock. Scientists expected a gentle nudge, a small proof of concept that might buy us some confidence for future planetary threats. What they got instead was a masterclass in cosmic physics that exceeded their wildest calculations and fundamentally changed how we think about defending Earth from asteroid impacts. Impact results analysis. The cosmic equivalent of hitting a home run when you were just trying to bunt. When the dust literally settled after DART's kamikaze mission, astronomers pointing their telescopes at Dimorphos couldn't believe what they were seeing. The Hubble Space Telescope and ground-based observatories worldwide detected something that made every planetary scientist do a double-take. This wasn't the gentle tap they had modeled in their computers. The asteroid's orbital period had shifted by an astronomical 32 minutes, not the modest 73 seconds they had predicted. That's like expecting to move a boulder an inch and accidentally launching it across the parking lot. But here's where the real detective work began. The impact results analysis revealed that Dimorphos had essentially turned into a temporary comet, spewing out a massive debris plume that acted like a natural rocket engine. This wasn't just impact physics. This was discovering that asteroids could become their own propulsion systems when hit just right. The momentum transfer was 26 times greater than expected, meaning NASA had accidentally stumbled upon a planetary defense cheat code. Scientists frantically recalculated everything they thought they knew about asteroid deflection, realizing that a relatively small spacecraft could potentially redirect city-destroying space rocks with far less effort than anyone had dared hope. The implications were staggering. Humanity's cosmic insurance policy had just gotten a massive upgrade, and all it took was one perfectly executed space crash. Momentum enhancement discovery. Sometimes the most incredible discoveries happen when your experiment works too well. The momentum enhancement discovery from DART's impact wasn't just a pleasant surprise, it was a complete game changer that sent shockwaves through the planetary defense community. When scientists analyzed why Dimorphos got knocked around like a cosmic pinball instead of just gently nudged, they uncovered physics that Hollywood couldn't have written better. The secret ingredient? That spectacular debris cloud wasn't just pretty space fireworks, it was functioning as an improvised rocket engine, blasting material away from the asteroid and creating additional thrust that multiplied the deflection effect beyond anyone's wildest dreams. This momentum enhancement effect revealed something extraordinary about how kinetic impactors actually work in the real universe versus computer simulations. The ejected debris acted like exhaust from a rocket, pushing Dimorphos in the opposite direction with tremendous additional force. It's like throwing a baseball and having it somehow gain speed mid-flight. Completely counterintuitive but absolutely real. The 26-fold multiplication of expected results meant that future planetary defense missions could potentially redirect dangerous asteroids using much smaller spacecraft than previously thought necessary. Scientists realized they had witnessed something that could revolutionize how humanity approaches asteroid threats. Instead of needing massive, expensive missions to deflect city-killer asteroids, relatively modest spacecraft could potentially do the job thanks to this newly discovered physics phenomenon. The universe had just handed humanity a cosmic cheat code for planetary defense, wrapped up in the most successful space crash in history. Asteroid structure insights. Some asteroids are basically cosmic sandcastles waiting to fall apart. The asteroid structure insights from DART's encounter with Dimorphos completely shattered our assumptions about what these space rocks are actually made of. When mission scientists dove deep into analyzing why the impact was so devastatingly effective, they discovered that Dimorphos wasn't the solid, monolithic boulder they had expected. It was what researchers now call a rubble pile, essentially a loose collection of rocks, dust, and debris held together by nothing more than weak gravitational forces. This revelation explained everything about the spectacular 32-minute orbital change and why the debris plume was so massive. Think of it like the difference between hitting a concrete wall versus a pile of gravel. The energy transfer is completely different. When DART slammed into this cosmic rubble pile, it didn't just create a neat crater like punching solid rock. Instead, it excavated enormous amounts of material, launching chunks of Dimorphos into space and creating that dramatic comet-like tail that telescopes tracked for weeks. This discovery fundamentally changed how scientists classify near-Earth asteroids and assess potential planetary threats. The loose structure meant that kinetic impacts could be incredibly effective against similar rubble pile asteroids, potentially making planetary defense missions far more successful than anyone had dared hope. But it also raised new questions. How many potentially dangerous asteroids share this loose, fragmented structure? The answer could determine whether future deflection missions are routine procedures or complex engineering challenges requiring completely different approaches. Strategic implications. One successful space crash just upgraded humanity's survival odds by millions. The strategic implications of DART's overwhelming success rippled through every space agency and planetary defense program on Earth, fundamentally reshaping how we approach the cosmic threat of asteroid impacts. When the momentum enhancement discovery proved that deflecting dangerous asteroids could be 26 times easier than previously calculated, it wasn't just a scientific breakthrough. It was a species-level game-changer that moved us from theoretical planetary defense to proven, practical capability. Military strategists, space engineers, and government officials suddenly realized that protecting Earth from city-killer asteroids might not require the massive, expensive missions they had been planning for decades. The implications extend far beyond just building bigger rockets or spending more money. This discovery means that relatively small, affordable spacecraft could potentially redirect near-Earth objects that pose existential threats to human civilization. Space agencies worldwide began recalculating their planetary defense budgets, realizing they could potentially defend against multiple asteroid threats with the same resources previously allocated for single missions. The kinetic impactor technique went from experimental concept to proven technology overnight, giving humanity its first real planetary defense weapon that actually works better than designed. But perhaps most importantly, the success demonstrated that we don't need decades of warning to mount an effective defense. The momentum enhancement effect means faster, more responsive missions could potentially handle threats detected with shorter lead times, dramatically improving our cosmic security posture. Hera Mission planning. The real investigation starts now. While DART proved that humanity can successfully punch asteroids off course, the European Space Agency wasn't about to let this cosmic crime scene go unexamined. Enter Hera Mission planning, the detective work that will finally reveal exactly what happened when our spacecraft obliterated Dimorphos, and why the results were so spectacularly beyond expectations. Scheduled to launch in 2024, this follow-up mission will arrive at the Didymos system in 2026 to conduct the most detailed forensic analysis of an asteroid impact in human history. Think of Hera as the cosmic CSI team, arriving to photograph the crater, measure the debris, and piece together every detail of humanity's first successful planetary defense demonstration. But Hera isn't just satisfying scientific curiosity, it's gathering critical intelligence for future planetary defense missions. The spacecraft will precisely measure Dimorphos's mass, analyze the crater's dimensions, study the asteroid's internal structure, and determine exactly how much material was ejected during impact. This data is absolutely crucial because the next time we need to deflect an asteroid, it won't be a test. It could be the difference between civilization and catastrophe. Hera's findings will help scientists understand whether the momentum enhancement effect was a lucky accident or a predictable phenomenon that can be reliably reproduced. Armed with this knowledge, future deflection missions can be planned with surgical precision, ensuring that when humanity faces a real cosmic threat, we'll know exactly how hard to hit it. Planetary defense evolution. From asteroid hunters to cosmic guardians in just one successful crash. The planetary defense evolution triggered by DART's triumph represents the most significant shift in humanity's approach to cosmic threats since we first started tracking near-Earth objects. Before September 2022, planetary defense was largely theoretical. Scientists could model asteroid impacts, calculate trajectories, and propose deflection strategies, but nobody actually knew if any of it would work when push came to shove. Now, with real data proving that kinetic impactors are devastatingly effective, space agencies worldwide are completely rewriting their threat assessment protocols and emergency response procedures. The momentum enhancement factor isn't just being incorporated into computer models, it's fundamentally changing how we categorize asteroid risks and allocate planetary defense resources. This evolution goes beyond just updating equations and mission plans. Countries that never had serious planetary defense programs are suddenly investing in asteroid detection networks and deflection capabilities. The International Space Station partners are collaborating on advanced warning systems, while private companies are developing rapid response spacecraft that could be deployed within months rather than years. The success has also accelerated development of next-generation asteroid hunting telescopes and improved orbital prediction algorithms. Most importantly, the psychological shift is enormous. Humanity has moved from passive observers of cosmic threats to active defenders of our planet. We're no longer just hoping that dangerous asteroids will miss us, we now have proven technology to make sure they do. The age of planetary defense isn't coming someday. It arrived the moment Dimorphos got knocked sideways by human ingenuity. Mission success redefinition. Success isn't always about hitting your target, sometimes it's about completely redefining what success means. Mission success redefinition became the most unexpected outcome of the entire DART program, fundamentally changing how space agencies measure achievement in planetary defense missions. Before impact, NASA had already declared the mission a triumph simply for demonstrating that humans could accurately navigate a spacecraft across 370 million kilometers and hit a target the size of a football stadium. The primary objective was purely technological: prove the guidance systems work, test the kinetic impactor concept, and measure any detectable change in Dimorphos's orbit, no matter how small. Mission planners would have celebrated even a 10-second orbital shift as groundbreaking proof of concept. But the universe had other plans. When the 32-minute orbital period change was confirmed, it didn't just exceed expectations, it obliterated every benchmark scientists had established for what constituted mission success. This wasn't incremental progress, it was a quantum leap that forced mission planners to completely recalibrate their success metrics for future planetary defense operations. The 26-fold enhancement over predicted results meant that DART had essentially accomplished what multiple missions were designed to achieve. Space agencies worldwide began questioning whether their own success criteria were too conservative, whether they were underestimating human technological capabilities, and how to properly set goals for missions venturing into uncharted scientific territory. The redefinition cascaded through every future mission proposal, with engineers now expected to plan for spectacular success rather than modest achievement. Debris management and safety concerns. What happens when your successful space mission accidentally creates a cosmic mess? The debris management and safety concerns following DART's spectacular impact revealed that planetary defense isn't just about hitting asteroids, it's about dealing with the aftermath of turning space rocks into temporary comets. When Dimorphos got walloped on September 26, 2022, it didn't just change its orbit, it transformed into a debris-spewing machine that kept astronomers busy for months tracking every chunk of ejected material. ground-based observatories worldwide suddenly found themselves monitoring a massive cloud of asteroid fragments spreading through space, creating an unprecedented challenge in space situational awareness and collision risk assessment. The spectacular debris plume that made DART so successful also raised serious questions about future deflection missions near critical space infrastructure. The ejected material created a comet-like tail visible through telescopes for weeks, with chunks of Dimorphos scattered across thousands of kilometers of space. Mission controllers had to carefully track this debris field to ensure it posed no threat to other spacecraft operating in the region, while also studying its behavior to improve debris modeling for future planetary defense operations. This unexpected consequence highlighted a crucial gap in mission planning. While everyone focused on successfully deflecting the asteroid, nobody had fully anticipated the complexity of managing the resulting space debris. The lesson was clear. Future deflection missions targeting asteroids closer to Earth or near valuable satellites will need sophisticated debris mitigation strategies to prevent turning one cosmic threat into dozens of smaller ones. Precision requirements for real threats. Practice makes perfect, but real asteroids don't give you second chances. The precision requirements for real threats expose the sobering reality behind DART's celebration-worthy success. While humanity proved we can deflect asteroids, the margin for error when facing actual Earth-threatening objects is absolutely zero. Unlike the controlled experiment with Dimorphos, where scientists had years to plan and could afford to overshoot their deflection goals, a genuine planetary defense scenario demands surgical precision that accounts for every variable imaginable. The momentum enhancement effect that made DART so spectacularly successful also introduced a new layer of complexity. Future deflection missions must accurately predict how much debris each target asteroid will eject, because the difference between nudging a space rock safely away and accidentally hurling it toward a populated area could determine the fate of millions. The challenge intensifies when considering that every potentially hazardous asteroid has unique characteristics that could dramatically affect deflection outcomes. Rubble pile asteroids like Dimorphos might respond completely differently than solid metallic objects, icy comets, or loosely bound dust clouds. Mission planners now face the daunting task of developing deflection strategies that work across this entire spectrum of cosmic threats, all while operating under the pressure that failure means catastrophic impact. The years of advance warning required for successful deflection means that asteroid detection networks must identify threats earlier and with greater accuracy than ever before. One miscalculation in trajectory, timing, or target composition could turn humanity's greatest technological achievement into its most devastating mistake. That's how NASA turned one perfectly executed space crash into humanity's greatest planetary defense breakthrough. The DART mission didn't just prove we can protect Earth from asteroid threats, it showed us we're way better at cosmic billiards than anyone dared hope. But this is just the beginning of our journey into the incredible world of space exploration and planetary defense. If you love discovering how we literally punched an asteroid off course, smash that subscribe button and hit the bell icon so you never miss the latest mind-blowing space facts. Drop a comment below. What space mission do you want Space Facts to cover next? The universe is full of incredible stories, and we're just getting started.